Good afternoon, everyone. I'm Rahil Ahmed, an AI researcher and co-founder of explainX.ai, a startup based in New York City that focuses on explainable AI and is on a mission to truly enhance human AI understanding by building trust and transparency in today's black box machine learning models. I'm very excited to speak with you all about explainable AI and its growing influence in multiple industries. It is a topic that has really taken off in the past few years and will be a crucial element in helping us achieve singularity as we move forward using AI more and more in our lives. For this talk, we will be discussing explainable AI on three levels. First, I will share with you the need and motivation for understanding explainable AI. I will then share a few state-of-the-art techniques that data scientists in particular can use to truly explain their machine learning models. Lastly, I will share a small use case with you all that will help you understand how XAI can be put into practice. So let's begin with the need and motivation. Explainability is extremely crucial in systems that are responsible for carrying out mission critical tasks. For example, in healthcare, if scientists are relying on AI models to help them whether the patient will have cancer or not in the future, they need to be 100% certain of their diagnosis. Otherwise, this can result in patient's death, a lot of lawsuits, a lot of damage done in trust. Nature of this problem is so intense that explainability sits at the core of this problem. The data scientists and the human operators, in this case, the scientists and the doctors, they need to understand how the machine learning system is behaving and how did it come to a specific decision. Recently, Google made headlines when its AI failed to perform in the real world. It was responsible for screening diabetes patients for diabetic retinopathy, which can cause blindness if not really caught early. In the lab, it was great, but in real life, the response was not so positive, and nurses were not really happy with the results, especially because they had no idea how a specific decision was made. So it created a lot of confusion. This clearly shows us that our lab experiments need to leave the lab and be placed in front of humans for them to actually use it in real life, for us as data scientists to actually determine how useful they are. Even when a system fails, we should be in a position to pinpoint the cause of that failure and fix it as soon as possible. Today, when a system fails, the general answer is, I don't know, and we really want to change that. Let's look at another example which is quite relevant in today's society: inherent biases in machine learning systems. Just because of how someone looks, we can't attach stereotypes, especially when we're deploying ML algorithms to help us decide, and they can't be biased. This is the area where we need to truly understand how the ML system came to this conclusion, whether the model is fair in treating subgroups within the data, whether there was an issue collecting the data in the first place. So pinpointing to the specific area that needs improvement is highly critical, and this just strengthens our case for explainable AI. Another important domain that we specifically focus on is finance, or fintech in particular, due to the growing adoption of machine learning solutions for credit scoring, loan approval, insurance, investment decisions, and so on. Here again, there is a cost associated with wrong decisions by the machine learning systems. So there's a huge need to understand how the model actually works. So to tie it all together, using black box AI increases business risk and exposes the business to a deep downside. The reason why black box models are not desirable becomes more clear when we look at how the business functions as a whole. For the business decision maker, we need to answer the question of why they can trust our models and our recommendations. For IT and operations, we need to tell them how they can monitor and debug if an error occurs. For the data scientists, we need to tell them how they can further improve the accuracy of their models. And finally, for regulators and auditors, we need to be able to answer whether our AI system is fair or not. I hope you're all convinced until now on why explainability is necessary and essential to your businesses if you're using AI. If not, let's add another layer of motivation and a reason to care, which is government regulations and laws against discrimination. Recently, the European Union laid out the GDPR. California released its Consumer Privacy Act. That has put the AI systems in the spotlight. They need to be fair, they need to be transparent, explainable, and they need to ensure privacy. If you read the GDPR Article 22, it clearly gives the user a right for an explanation that affects them. And these are just the main ones that are out there, but there are so many growing regulations coming up in multiple different in countries. So we as data scientists and businesses operating on AI systems really need to take this seriously. Otherwise, we might be exposed to hefty fines, and no one in the business world likes to be fined. As a result, we want to design our AI products to ensure they're explainable. We need to have an explanation around the predictions on multiple different levels. They need to be compliant. We should be able to evaluate the model performance and measure it for compliance to help auditors and regulators. It can be monitored. We should be able to monitor the performance and fairness of the models as they help us make decisions for us. And they must be debuggable, which means that we should be able to diagnose and identify the root cause of failure to fix the errors, thus improving the overall model accuracy. So now, as we have laid the foundations down and we have our motivations clear, let's dive in and talk about explainability techniques. So explainable AI aims at providing clear and transparent predictions. An end-to-end AI system will provide decisions and explanations to the user, and ultimately will provide an automated feedback loop to constantly improve itself. So you have to remember that XAI is highly driven by feedback. So it's a two-way interaction between the human and the AI system. In the end, you should understand the why behind the model, impact of the model, where the model fails, and recommendations to follow. So currently there are two explainability approaches. The post-hoc explanation given an AI model, and you can have a global level explanation, and you can have an instance-based explanation, which means that you're explaining individual predictions. The second is you build an interpretable model, like logistic regression, decision trees, decision list. But we'll be focusing on the post-hoc explanation because they're much more advanced and much more versatile. Building an interpretable model sometimes costs us a lot of accuracy. So we will focus on post-hoc explanations, and to better understand the concept of post-hoc explanation, we need to understand the concept of attributions, because the post-hoc explanation is based on these attribution methods. So what is an attribution score? Attribution score is a score that model assigns to each feature that is proportional to that feature's contribution to the prediction. So for example, in a text sentiment model, our individual words will have an attribution score. For our credit score example, individual features like income, loan account, loan amount will have an attribution score. The attribution score doesn't really tell you the deep logic of the model, of how the features just come together, but they're very effective in telling you why the prediction was made. And surprisingly, these are extremely, extremely useful and a very effective starting point. By using attributions, we can debug the model prediction. We can generate an explanation for the end user. We can analyze model robustness, extract weaknesses from the model by identifying known relevant features getting more importance, and we can catch them beforehand. And we can extract rules from these models. If the model is good, then peek into the logic of the model more and extract the rules from the model so that we can better explain it. There are a lot of attribution methods. We won't go in much detail, but I will just briefly describe what each of them are so you can actually familiarize yourself with them. So the number one is an ablation method, which is basically you drop each feature and attribute the change in prediction to that feature. It's a very simple and it's a very intuitive method, but sometimes it can create unrealistic inputs and can be computationally extremely, extremely expensive. Then we have very widely used gradient-based methods, which is basically just feature value multiply its gradient. And we examine gradients at several different points. That is why a lot of people today are using integrated gradients, which is that you take gradients at several points and then you ultimately take the average and you get more plausible looking attributes. And the best part about gradient-based methods are that they capture the sensitivity of the output with respect to the feature. Then we have score backpropagation methods that are specifically for neural networks, in which we redistribute the prediction score through the neurons in the network. Then we have local surrogate model-based methods, which is basically we just create a linear separator, and we train a linear separator which is very close to the assigned, which basically assigns weight according to how important the feature, how close the feature is to the linear separator. And those attribution scores are just the linear coefficients of that specific linear model. And then you have Shapley value-based methods. It's a very famous and it's based on game theory. And it's basically a fair way to distribute the gain to the players. And in this case, the players are basically the features. So it's a very interesting model that that looks at how important the feature is to a specific prediction, and then accordingly provides the specific score. And for each prediction, that score varies. So it's a very versatile method. It is not a complete list, and I won't bore you with all the mathematics behind this, but these methods are extremely useful and valuable to use. However, these alone will not provide you with a complete picture. We need to understand how features interact. We need to run prototypical analysis to identify similar prototypes. We need to run scenario analysis to look at the subsets within the data set and generate contrastive explanations to further create a narrative around the entire use case. There's so many buzzwords, but let's understand what each of them does basically. Number one, we have the partial dependence plot. It's a very simple one, very widely used. It shows the marginal effect one or two features have on the predictive outcome of a machine learning model. Very simple one. We'll further go into the detail of it in a few minutes. You also have summary plot. It's a very dirty looking plot, but it's a very effective one because it combines feature importance with feature effects. Each point on the summary plot is an impact value or an attribution score for a feature and an instance. And we can read this that whenever the value of the feature goes up, its impact on the prediction is either negative or positive. And so by identifying this, we can dive in deeper to identify scenarios where the feature has a positive impact, the value is also high, but the prediction is bad. So why is that happening? We can actually go deep, dive in and understand in much more detail. Then you have scenario analysis, a very simple approach. With scenario analysis, we can slice the data into various subsets and see how the model has performed. Is there anything we do not like or something that is inherently wrong? We can easily catch it. For example, maybe for applicants whose age is greater than 60, the model is biased because the data that it contains has more defaults than approved. So catching that beforehand is extremely crucial for us. Then you have a very interesting approach that is overlooked by a lot of data scientists today, which is a prototypical analysis. Prototypical analysis is basically we try to justify the model's prediction by identifying similar data points within the data that were influential in the model's logic. So here we can see that Dan had a very similar profile to Alex, Bob, and Red. And all of those three other customers were denied. Therefore, the model denied the application for Dan as well. So it's a very easy to understand explanation when we're presenting our narrative to the business user. Then you have contrastive explanation, another technique that is very, very overlooked, which helps you understand which features, if changed, will ultimately change the prediction or might keep it the same. It uses two concepts, pertinent negatives. So pertinent negatives identify a minimum set of features, which if altered would change the classification or the prediction of the original input. Pertinent positives, on the other hand, are identify a minimum set of features and their values that are sufficient to yield the original prediction or input classification. So for example, for our credit score example, if Dan can increase his credit card score from 500 to 600, can decrease his risk estimate from 70 to 50, and work one more year, he will be qualified for a loan. So simple. So by using contrastive explanations, we can provide recommendations to our customers and business users on what they need to change in order to achieve a desirable outcome. So I hope I did not really overwhelm you all with all these technical details and jargon. If I did, I hope to make it up to you by informing you that that at explainX.ai, we recently launched an open source library written in Python that helps data scientists simply plug in their models and use an interactive dashboard to create a narrative for their models. And so to continue on that, we will do a loan application use case by using the library. So let's get started and see XAI in practice. So a little bit about explainX.ai is explainable AI engine. We're basically helping data scientists understand, explain, validate any black box machine learning model to ensure trust and transparency in AI systems. And we're doing that in just one line of code, all within their Jupyter notebook. So instead of utilizing all techniques one by one, trying which works and which doesn't, we have compiled the state-of-the-art in an open source Python library for accelerating the development of XAI among the data science and AI community. So here's what the use case is. This is a loan application approval use case in which we are building a model that will help us predict credit risk. And the data set that we're using is a Hello data set that is available from FICO. So a user comes in, requests for a loan, the bank queries it into the AI system, rejects it, and tells the user that it got rejected. Now the user wants to know why, how, and what should I do about it. So a little bit technical to initiate. If you're a data scientist, if you have a Jupyter notebook, you can actually follow this example to like do it on your own as well to initiate. So we will install all the relevant packages and import dependencies. We will load the data set and initiate the cat boost classifier model, because that is the model that we're trying to explain right now. After the model building is complete, we will initiate the explainX function and we will begin explaining the cat boost model. So you have to remember that we are using Shapley value attribution method at the core of the library, and that will help us understand the overall logic of the cat boost model as well. So how this actually, so first we have the global feature importance. As we can clearly notice that MSIN's most recent inquiry, percent trades, and average minimum file are the top 3 high impact variables. This basically actually gives us a general idea of what the model thinks our top variables are that we need to pay special attention on. And basically, how does this help? It helps us to identify important features on a global level or by using the entire data. We can actually check out if the importance of, if the order of importance is right or wrong, if it matches our intuition or not. If it doesn't, why doesn't it? It helps us identify top features that play a crucial part in model prediction. Just like I mentioned, the top 3 parts, we'll have a special attention to these top 3 variables. So then we have to check a global feature impact. Then after we know what the top features are, we have to understand whether a feature has a negative impact or a positive impact. So by looking at the graph above, we can understand that percent trades with balance and new fraction installed burden, they positively impact the prediction. This means that if the prediction is good, if the prediction means that approves the loan for a specific customer, these 2 variables will play a vital part in maintaining that prediction. But if we look at external risk estimate, it has a negative impact, which aligns with our intuition as well. This means that if the prediction is approved and we keep on increasing the external risk estimate, we will end up flipping up the prediction to deny. So this actually helps us identify further whether a variable has a negative or a positive impact, and helps us identify feature influence on the predictions. Then let's look at the feature interaction by using a partial dependence plot. We can clearly spot a pattern here. When the value of external risk estimate is between about 40 to 60, we actually have a lot of bad candidates. Now, the question is, why is that so? And this is an interesting trend to explore that we can easily do by simply choosing maybe a third variable, like prediction in this case, to help us further explore how it's working. And we can clearly see that between 40 and 60, we have bad candidates, but as you constantly increase risk estimate, there's a huge chunk of bad candidates that we can find at the top as the external risk estimate is extreme. And we can also see that there are also negative external risk estimate. We can look if it's an error in the data, if there might be issues such as outliers. So we can actually go around and address them. And how does this basically help us? So it helps us understand marginal effects of changing the value of each variable, that as I increase my external risk estimate, my prediction changes by this much. It also helps us identify correlations and interactions among different features to help us how different features interact with each other. So once we have that done, we can explore different scenarios to see how the model performs within different data sets. And by using explainX, you can actually apply data filters within the data table without any SQL queries and explain multiple instances and scenarios very easily. So for example, here we are trying to see, tell me about the instances where the age was greater than 70. We want to identify whether a model was biased towards a specific age group. And by slicing and dicing, we can actually figure that out. So this basically helps us identify patterns within subgroups and helps us identify how different subgroups perform to better cater to their needs. To summarize, then we have the explanation on a very individual level. So here's a customer, and we want to summarize what we actually learn about this customer. So here we can actually see that for this specific prediction point, for this specific customer, percent trades with balance had a very positive impact on the outcome, where number of satisfactory trades had a negative impact on the outcome. This is also called decision logic that the model took to arrive to a decision, and clearly this tells us which are the top 3 and the bottom 3 features that we really need to look at to identify why the model said what it said. And then we can further explore these top three and bottom three features to see what the user can do in order to get the loan approved. This will provide them, we will provide them with recommendations on, increase your X variable by this much and you'll get the loan and stuff. And now we start talking about actionable insights, providing them with actionable recommendations that they can do, thus improving our customer experience as well. So this individual level prediction basically helps us answer why was a customer loan rejected in the first place? What is my model doing across multiple different variables for this specific customer? And what variables should my customer focus on to improve their outcome? Lastly, to sum it all up, after explaining on an individual level, we can generate similar profiles to further support our analysis, to further support our narrative. So in this case, we can see that the first user is 34% similar, the second user is 31% similar, the fourth user is 32.7% similar to the applicant that we're trying to explain. So there are a lot of variables that overlap. And now we can say that, all right, so I understand why the model was inclined towards rejecting the application for Dan. It's because that it has these many attributes that are similar to user 0, these many attributes that are similar to user 1, and that is why by combining all of this, the model actually made the prediction that don't approve the loan for this guy. Now by combining all these methods that I just described, we now have a narrative of how our model works and why it arrived at a certain decision. Explaining individual predictions by using similar profiles helps us identify other similar customers that exist in our data set. It also helps us identify variables and their values that were similar to the customer that we're trying to approve the loan for or not. And it also helps us understand how the model is thinking. So challenges, right? So we're working around the clock at ExplainX to innovate in this area, but still challenges remain. The biggest challenge is scalable XAI in production is still very challenging as we're getting a lot of different data, we're increasing in data sets. It's a wide variety of data that we're collecting. So using that in real time is extremely challenging. And then a lot of data scientists trust black box AI just because they're really, really accurate sometimes. And that needs to change. They need to start thinking, they need to start being more skeptical about the AI models and need to find reason to more and more trust these algorithms by building explainability in them. And explanations can vary, so data scientists need to be on top of their game and they need to be really good storytellers in order to make a very compelling case about their recommendations. And another challenge is that making sense of these explanations is quite an iterative process. As I said, it's a feedback, it's a two-way road that you have to go back to the domain expert, you have to come back, you have to constantly improve your model and make sure that it aligns with whatever your mental intuitions are. And then building and adding more and more approaches is extremely time consuming, but we understand that it's extremely, extremely important. So to sum it all up, we learned that explaining models is extremely crucial. Data scientists can use the explainX Python library in seconds to start explaining models. We learned a very good interactive user interface is required for interactivity and for a very compelling narrative. And we started that building a narrative around the entire model, how the model performs, is extremely crucial in explaining the logic behind the model. I hope you learned a lot from this talk. And thank you so much for all your attention. Feedback is always encouraged. It's extremely important. It helps us improve. So feel free to reach out to me on my email and start explaining your black box model with ExplainX. It's an open source library that we recently just launched. The link is here on GitHub. And I really hope you enjoy and you build explainability in your AI systems and make better decisions. Thank you so much.